Hello, and welcome to this presentation, Testing ILS with the SMA100B. In this presentation, we'll explain how to generate the three main components of ILS, Localizer, Glideslope, and Marker Beacon, using a Rohde Schwarz SMA100B analog signal generator. This presentation assumes a general technical familiarity with ILS signals. If you're not already familiar with ILS, you might want to watch the presentation Understanding ILS before proceeding with this presentation. To access the different avionics modulation types on the SMA100B, including ILS, first select the modulation tile, then choose Avionics Standards from the list of available modulation types. Configuration for all three ILS components is found under the ILS tab. In the General tab, you can select the ILS component you wish to generate, Glideslope, Localizer, or Marker Beacon. Remember that the SMA generates only one of these signals at a time. When you finish configuring the ILS signal parameters, don't forget to enable the modulation as well. Let's start with Localizer signal generation. Note that many of the concepts and terms used in Localizer signal generation are also used in Glideslope signal generation. The first step in configuring a localizer signal is specifying the localizer frequency. This can be done in two ways, either by directly specifying the frequency in units of megahertz, or by entering it as an ICAO channel number. Here, 109.5 MHz corresponds to ICAO channel number 32X. Basic localizer signal properties are set up under the Signal tab. In normal operating mode, both the 90 and 150 Hz lobes are generated. It is, however, possible to change the operating mode and have the SMA only generate one of the lobes. The frequency of each lobe can be changed individually, and the left-right phase parameter controls the phase difference between the signals in each lobe. Normally, none of these parameters need to be modified. The final parameter is DDM polarity. To understand what this means, we first need to explain what DDM, or difference in depth of modulation, means. Both lobes of the localizer are AM modulated, the left lobe at 90 Hz and the right lobe at 150 Hz. The modulation depth of each lobe is different depending on our position within the lobe. On the runway center line, both lobes have the same AM modulation depth of 20%. As we move to the right of the center line, the AM modulation depth of the 150 Hz lobe increases, and the AM modulation depth of the 90 Hz lobe decreases. For example, at this point, the modulation depth of the 150 Hz lobe has increased to 30%, and the depth of the 90 Hz lobe has decreased to 10%. And at the far right edge of the localizer pattern, we see the 150 Hz lobe at 40% AM modulation depth with a zero modulation depth, so to speak, on the 90 Hz lobe. The localizer determines position deviation from the center line by using the difference in the depth of modulation between these two lobes. Mathematically, we can say the difference in depth of modulation is the measured 90 Hz AM modulation depth minus the measured 150 Hz AM modulation depth, divided by 100. The order of the terms in the numerator, that is, which number is subtracted from the other, is defined by DDM polarity. So an aircraft that's exactly centered on the runway center line will see the same AM modulation depth on both lobes, and difference in depth of modulation, or DDM, will be zero. Moving to the left of the center line, that is, more into the 90 Hz lobe, causes DDM to increase, or become more positive. Moving to the right of the center line, or more into the 150 Hz lobe, causes DDM to decrease, or become more negative. These changes in DDM are what cause the needle to move right and left on a localizer dial. DDM is closely related to something called fly mode. Fly mode is simply an indication of which direction the pilot needs to fly in order to intercept the localizer center line. This is based on the current value of DDM. If fly mode shows right, this means that the 90 Hz lobe is dominant, DDM is positive, and therefore the pilot must fly right to intercept the center line. If the fly mode shows left, then the 150 Hz lobe is dominant, DDM is negative, and the pilot has to fly left to center the aircraft with the runway. Note that fly mode on the SMA is really more of an indication than a configuration parameter. You can also switch fly mode manually from right to left, which simply reverses the sign of the DDM values. In other words, the plane's position would be swapped around the center line if fly mode were manually toggled. Difference in depth of modulation can be expressed in three different ways: DDM depth, which is unitless, DDM logarithmic, which is in units of dB, and DDM percent. The conversion between units is done using these simple formulas. On the SMA, changing any one of these values will update the other values automatically. One additional way that DDM can be expressed is in terms of current. The deflection of the localizer needle is controlled by the current passed to the display device, that is the gauge or dial, and this current is a function of the measured DDM. For localizers, the current is calculated using the formula DDM microamps equals DDM percent times 967.75 microamps. For example, if DDM is 0.2, then the corresponding DDM current would be 193.6 microamps. Changing the current changes the DDM and vice versa. If you're wondering where this conversion factor comes from, it actually corresponds to 150 microamps at a DDM of 15.5%, which is normally seen at the outer extremity of the ILS course sector. Keep in mind that DDM current is just another way of expressing or specifying the DDM created by the SMA's RF output signal. The SMA doesn't actually produce a DC current out signal. The only remaining localizer amplitude settings are related to the sum of depth of modulation, or SDM. Sum of depth of modulation, as the name implies, is simply the sum of the modulation depths of each lobe. The default value for localizer signals is 40%. The parameter DDM-SDM coupling is related to how DDM and SDM are related. If fixed DDM is used, then difference in depth of modulation doesn't change when sum of modulation depth changes. If coupled to SDM is chosen, then the absolute values of DDM will change if SDM is changed. Don't worry if this seems somewhat obscure. Normally these values can safely be left at their default values. The last tab in localizer configuration is COM ID. The COM ID signal allows the pilot to audibly identify the localizer using Morse code. Code is the transmitted Morse code sequence. Note that for localizers, this usually begins with the letter I to avoid confusion with the ID from VOR stations. Period defines the interval between transmissions of the Morse ID. Frequency controls the pitch of the demodulated signal, and depth is the AM modulation depth. Finally, time schema and dot length control the timing and spacing of the dits and das used in the Morse code ID. These can be left at the standard values or defined by the user. Now that we've covered localizer, let's move on to discussing Glideslope. As previously noted, most of the concepts in localizer apply to Glideslope signals as well. The first step in configuring a Glideslope signal is specifying the Glideslope frequency. As with localizer, this can be done either in units of megahertz or as an ICAO channel number. Here, 332.6 MHz corresponds to ICAO channel number 32X. Remember that localizer and Glideslope frequencies are paired, so the same ICAO channel, 32X, corresponds to a VHF localizer frequency of 109.5 MHz. The Glideslope signal properties work the same way for Glideslope as they do for localizer. They allow you to change the frequency of the two lobes, turn one of the lobes off, and change both the phase between the lobes, as well as define the DDM polarity. Again, these are completely analogous to the signal parameters for localizer. Glideslope is also analogous to localizer when it comes to the difference in depth of modulation, but with one important difference. The standard AM modulation depth along the Glideslope is 40% for each lobe, as opposed to the 20% standard modulation depth used in localizers. The formula for DDM is, however, the same in both cases. As with localizer, an aircraft on the Glideslope will see the same depth of modulation from both lobes, and DDM will be 0. Flying above the Glideslope moves the plane more into the 90 Hz lobe, and DDM increases. Flying below the Glideslope moves the plane more into the 150 Hz lobe, causing a decrease in DDM. Similar to the way that the localizer works, the Glideslope needle is controlled by these changes in DDM. The fly mode in Glideslope works much the same way as it does for localizer. If the difference in depth of modulation is positive, this means the aircraft is above the glide slope and the pilot should fly down. Conversely, if DDM is negative, this means the aircraft is below the glide slope and the pilot should fly up. And unsurprisingly, most of the other glide slope amplitude settings on the SMA have the same meaning or effect as their localizer counterparts. There are, however, two differences to make note of. First, as mentioned before, the default sum of depth for glide slope is 80%. This is different from the default value of 40% in localizer. The second is that the DDM glide slope current is calculated using the scaling factor 857.125 microamperes. This is different than the localizer, which uses 967.75 microamperes. Now it's time to look at marker beacons. Compared to localizer and glide slope signals, marker beacon signals are very easy to understand and very easy to configure. To configure a marker beacon signal, start by selecting marker beacon as the ILS component. Since all marker beacons typically operate at 75 MHz, the default carrier frequency of 75 MHz should work in most cases. Because they all operate on the same frequency, the inner, middle, and outer markers are differentiated by both the tone or frequency of their signal, as well as by the pattern of sounds. The outer marker uses a 400 Hz tone sent as a pattern of dashes. The middle marker uses a 1300 Hz tone sent in a dot-dash pattern. And the inner marker uses a 3000 Hz tone sent as a series of dots. The tone is chosen using the marker frequency parameter and is sent continuously by default. The appropriate intermittent pattern of dots and dashes is turned on by enabling the pulsed marker parameter. Finally, note that COM-ID is not used when generating marker beacon signals. Let's summarize the main points regarding ILS signal generation. The Rohde Schwarz SMA100B analog signal generator can be used to generate all three components of ILS: the localizer, glide slope, and marker beacon signals. Note, however, that only one of these modulation types can be active at a time. The most important parameters when configuring ILS depend on the signal type. For localizer and glide slope, difference in depth of modulation, or DDM, is the most important, since this provides the left-right or up-down guidance to the ILS receiver. For marker beacons, the beacon frequency and the associated pattern of dots and dashes are what distinguish between the different beacon types. Remember that many of the parameters used in localizer and glide slope configuration are often the same or very similar in meaning and function. This concludes our presentation, Testing ILS with the SMA100B. Thanks for watching.